In this video, we discuss how to solve differential equations by separating the different parts. These are called separable differential equations. This is geared for a Calculus 2 course and is based on the OpenStax Calculus textbook, Volume 2, Section 4.3, Separable Differential Equations. In order to understand how to solve a differential equation by separating the parts, we need to recall that dy dx is Leibniz's original notation to replace the first derivative y prime. Because we can write dy dx in this format, we can abuse the notation, and again, while not technically correct, we do it because it works. The dy dx is not in fact a fraction, it is the derivative operation, but the genius of Leibniz's notation is that by treating it like a fraction, we can perform operations that in fact are mathematically correct and do lead to the correct answer 100% of the time. What we do in this case is we take the y prime and we divide both sides of the equation by it to get 1 over y prime on the left. Then we separate the differential dy from the differential dx in the notation for the first derivative. We'll leave the dy differential on the left to accompany the derivative of y prime. On the right side then, since dividing by y prime left a positive 1 behind, this gives us dx by itself now on the right. In this way, we have separated the y variables and the differential dy from anything with an x variable and the differential dx. Now, this cannot always be accomplished. In fact, there are particular kinds of equations in which this is possible, and there are equations in which it is simply not possible. The point of the differential equations course is to learn what to do in the different situations. Separating is one of the first techniques that you'll learn, again, in ordinary differential equations. This applies, of course, to a first-order differential equation, meaning that in order to do this, you can't have y double prime. You must have only y prime, or the first derivative. This also means that you must be able to separate the y and y prime variables from the x and the differential dx. This is, of course, one of the easiest methods to solve a differential equations course, which means that you will not see it terribly often in an ordinary differential equations course, but you will see it often enough that it is a technique you will need to know very well. In general, we say that the differential equation can be separated if it can be written in this format. Solving for the first derivative of y gives you a function in terms of x multiplied by a function in terms of y. If it can be written in this format, then we can separate it and we can call it separable. Here are some examples of separable and non-separable differential equations. If we're looking at this, you can tell that, of course, Word does not like my use of non-separable. It does not consider that to be a word. Mathematicians, however, are quite accustomed to this. We consider it a word. Examples of separable and non-separable. In this particular case here, I can separate it. I have dy dx on one side by itself. The opposite side is a multiplication of factors involving y and x. Now you may say, how on earth can you separate e to the 3x plus 4y power? Simple. You simply will use your properties that you've learned in your college algebra class to rewrite that exponential as e to the 3x times e to the 4y. Remember that when the bases are the same, you add the powers. So this factor here is equivalent to this factor here. That would let me then write the x attached to e to the 3x and the y squared attached to e to the 4y. Now technically they're all attached to one another because this is, of course, a product, and the order in which you multiply things does not affect the product. This does let me, however, separate them into a function involving x and a function involving y, then they're being multiplied together. So this is what we consider to be a separable differential equation. This equation here, many students mistake for being separable because clearly the function of x, which is sine x, and the function of y, which is simply y itself, are already separated. And indeed they are separated, but they're separated by addition and not multiplication. Recall that your definition of separable means that the two functions must be multiplied together, because what we will be doing in order to solve it will be dividing them one side and the other. And if we don't have multiplication, we cannot get division. And if we cannot get division, we cannot get them attached to the correct differential. The multiplication is important. Now, an ordinary differential equation in which the independent variable does not appear is something that's called autonomous. If we consider x to be the independent variable, that means that that differential equation does not actually have an explicit x squared, or anything involving x in the differential equation. Those particular types of differential equations are very easy to separate and are usually solved using this method. However, as you've seen in this example up above, that is not required in order to use this technique. It's simply easier in that case. I simply love differential equations, so it's hard for me to resist giving you more information. I do want to talk at least a couple of seconds about what an equilibrium solution is, because your book really sort of glosses over some of this. Remember from Calculus 1 that the zeros of the first derivative, when f prime of c is equal to 0, are considered critical values or critical points. They're not necessarily the extrema values. In other words, you don't have to have a maximum or a minimum at a critical point, but they are places where it could occur. When you're thinking about them in terms of a differential equations class, these are called both stationary points and equilibrium points. Why is that the case? Well, if you know that it is the case that the derivative at that point is 0, then the solution y equal to that constant becomes a constant solution of the differential equation. And we call that an equilibrium solution. Because it is a constant equation, it is a horizontal line when you graph the solutions. Now we're skipping that in this particular course, but it will be something you'll spend a lot of time on when you get to your differential equations course. To find those equilibrium solutions, you'll have to use a different technique. You cannot use the techniques that we learn to find the general ones. To find an equilibrium solution, you solve the differential equation for dy dx. This is okay because remember, when we're looking at our format up here, we want to know that we can solve it for dy dx to get a function of x multiplied by a function of y. So it's not wasted effort, even if you don't find one. In this case, after solving for dy dx, you'll be able to determine whether or not the opposite side is the product of a function of x times a function of y. If it is, you'll be able to separate to find the other solutions. To find the equilibrium solution, you will locate the factor that is a function of the variable y. In other words, ignore the parts that are simply the function of x. This is the g of y and what we did above. You'll set this function of y equal to 0 and solve. Those would be the solutions that are called equilibrium solutions. Looking back at our example here, what that means is I would take this part here, e to the 4y times y squared, and set it equal to 0. I would ignore this factor here that is a function of only x. Now, e to a power can never be 0, so the solution, the equilibrium solution, can't come from e to the 4y, which means it has to be coming from y squared equal to 0, which means y is 0. This, of course, is the trivial solution, which we talked about earlier as a singular solution. Now let's take a look at how we can apply this. After you have identified any constant solutions or equilibrium or stationary solutions, then we want to get all of the y's on one side of the differential equation. This assumes that you have already discovered that it can be separated, meaning that you solved for dy dx and you observed that you could separate the pieces, the factors, into factors of only x and factors of only y, and that they're multiplied together. If you can do that, then you'll move all the y's to one side and you'll have them multiplied by the derivative dy dx. That's the first derivative. Basically, since you originally solved for dy dx, trying to find the equilibrium solutions, this means that after doing that, you will divide both sides by whatever that function of y was. That will leave all of your x's on the opposite side of the differential equation from the first derivative dy dx. Then you will abuse the notation by taking the denominator differential dx and multiplying it on both sides. I know it sounds crazy. It's not a fraction. It is an operation, the derivative operation. But it works, so we do it. Then you integrate both sides with respect to their differential variables. You'll combine the two constants of integration into one. It's typically written on the side with the x because, of course, we're trying to find y. That is, if you look at steps 2 and 3, what's happening is you're taking this form of the differential equation where you've isolated dy dx and determined that you can write it as a function of only x multiplied by a function of only y, and you've rewritten it in the form where the g of y gets moved to the left in the denominator, and the differential dx gets moved to the right and gets attached to the function of x. Then you will integrate both sides. The left will be integrated with respect to y, and the right will be integrated with respect to x. They'll both generate a constant of integration, but we'll combine them all into the constant of integration that we get from the right. Here are the steps that your textbook recommends on applying the technique of separation of variables. First, you need to solve for dy dx. They don't actually have that in here. I would add that as a step 0. Solve for dy dx. Then find the factors that make g of y equal to 0. These would be those constant solutions or equilibrium solutions. Then, once you've done that, divide both sides by g of y so that you can get all of the things related to y on the left, and multiply both sides by the differential dx so that you can get all things related to x on the right. Integrate both sides of the equation with respect to the individual differentials that are present on that side. When you're done, try to solve the equation for y. If you can, you get an explicit solution. If you cannot, your solution will be an implicit solution, meaning implied. If there's an initial condition, substitute those values into x and y in the equation and solve for the constant. Now, again, down here at the bottom, you need to remember that it's not always possible to get an explicit solution, and that on occasion, you'll simply have to leave it as an implicit solution. Let's take a look now at example 1. It says, find the general solution to this differential equation. The first thing I need to do, which of course the textbook left off, is solve for dy dx. So I need to isolate the dy dx on one side. Typically, we leave it on the left because we're going to want the differential dy on the left because, well, we just like it there. We like to have y equals, not stuff equal y. Is it wrong the other way? No, it just looks weird. In this case, that means that I'm going to rewrite this as e to the negative y plus e to the negative 2x minus y, all divided by e to the x times y. Now you may be a bit bothered by that addition in the numerator, and in fact you should be, because we know that we have to separate these and isolate them so that we can get a function of only x multiplied by a function of only y. In order to do that, we're going to have to apply some tricks here. The first trick we want to apply from our algebra class is to separate this term e to the negative 2x minus y power into two factors, e to the negative 2x times e to the negative y. That will be step 1. This gives me e to the negative y plus e to the negative 2x times e to the negative y. We'll leave the denominator alone for now. In the next step, I'm looking at the numerator. I've got to turn this into things that are multiplied only. That means that addition has got to be buried inside of a factor, buried in parentheses. I'm going to look at it and see if I can find a common factor, and I can. I see that e to the negative y is present in both terms, so I'll factor that out. This gives me e to the negative y times 1 plus e to the negative 2x, all divided by e to the x times y. Now, notice that in this case, the e to the x is written first and the y second. But when I look at these factors in the numerator, the one related to y is written at the beginning and the one related to x is at the end. Since multiplication is commutative, let's just turn this around and write it as y times e to the x. That gives me my two functions, one of y and one of x. To emphasize this, we'll write them separately. This means that I can now write dy dx equal to e to the negative y divided by y times 1 plus e to the negative 2x divided by e to the x. This is my function in terms of only y. This is my function in terms of only x. To find the equilibrium solutions, also called constant solutions or stationary points, I want to take just the function of y and set it equal to 0. This is e to the negative y divided by y. Does it equal 0? A negative exponent means it can be moved to the denominator, which leads to the equation y e to the y equal to 0. That is impossible. There is no value of y that will lead that to be true. The only way to make a fraction equal to 0 is for the numerator to be 0 and the denominator to be not 0. In this case, the numerator is 1, and 1 will never equal 0, which means it's not possible, and there are no equilibrium solutions here. That's okay. This isn't wasted effort. Because we've done this, we have determined that in fact we do have a function of y multiplied by a function of x. In order to separate it, I'm going to take this function of y and divide both sides of the equation by it so that it moves to the left. I'm going to abuse the derivative notation and take the differential dx and move it to the right. That would be our next step. In order to accomplish that, you may want to think of the e to the negative y instead in the form of 1 over y e to the y. In order to move it then to the left side, I'd multiply both sides by y e to the y. This leads me to write y e to the y dy equal to, on the right-hand side, I still have 1 plus e to the minus 2x over e to the x. 1 plus e to the minus 2x over e to the x, now times the differential dx. The next step, of course, is to integrate both sides. The left will be integrated with respect to its differential variable, which is y. The right will be integrated with respect to its differential variable, which is x. This is one of the reasons I've been hounding you for 2 semesters now about not leaving the differential off. It is crucial when you get into differential equations and multivariable calculus. Now, how are you going to integrate this here? Yeah, you got it. We need integration by parts again. You may want to pause the video here, work out the integrals yourself and then turn the video back on and check your answer with mine. Picking up where we left off, that means that you need to integrate the left side with respect to y and the right side with respect to x. Now, y to the y is an integration by parts, which I have solved using the tabular method. If you're not familiar with the tabular method, then simply go into my Calculus 2 playlist and find the videos that cover the tabular method of integration by parts. It is a by far simpler formula for doing integration by parts that always works. In this case, it leads us to y to the y minus e to the y for the value of the integral on the left. There is also a constant of integration, but we'll roll it into the constant of integration we get from the right side. The right-hand side indefinite integral is a rather tricky u substitution. The key to knowing what to do is to rewrite this problem here instead of as the ratio of two functions of x as the product of two functions of x. That lifts the e to the x to the numerator and becomes e to the negative x. Then you need to recognize that if you squared that, you would end up with e to the negative 2x. That leads you to make the substitution that u is e to the negative x, so u squared is that e to the negative 2x. Taking the derivative, of course, simply gives you the same function with a negative 1 as a constant with the differential dx. That means that when you solve for dx, you get negative du over e to the negative x. But since e to the negative x is our value of u, you can write dx as negative du over u. When you substitute these values into the indefinite integral in place of e to the negative x, e to the negative 2x, and dx, you get the integral of negative the quantity 1 plus u squared with respect to u. This leads to the following result as the antiderivative. This plus c here does represent the constant of integration from the indefinite integral on the right, but will also roll into it the opposite of the constant of integration from the left. Continuing down and replacing u again with e to the negative x, I arrive at this solution here. Now the next step would be solve for y. However, y is present both as a factor and as a power inside of an exponential factor. That means that there is no way I can get my hands on y and isolate it. Because of that, I will have to leave it in this format, or you could move all of the terms related to x and y to the left and leave just the constant on the right. This is a general solution, but it is an implicit one because I was not able to solve for y. Let's now look at this initial value problem. dy dx is equal to the binomial factor y squared minus 1, all divided by the binomial factor x squared minus 1. We have an initial condition, which is that when x is equal to 2, the y variable is equal to 2 as well. Let's see if we can separate it. If we can separate it, then we can also look for the equilibrium solutions at the same time. It's already been solved for the first derivative dy dx. Remember that separating only works on first order ordinary differential equations. In this case, in order to get the remaining part separated, what I'll write is dy dx is equal to 1 over x squared minus 1, which will be my function in terms of the variable x, times y squared minus 1, all divided by 1, which will be my function in terms of the variable y. Now, to find the equilibrium solutions, I need to take just the function of y and set it equal to 0. So when we're looking for those equilibriums, remember that you ignore the function of x. To find those equilibrium solutions, take g of y and set it equal to 0. This means y squared minus 1 equals 0, which of course leads to y squared equal 1, or y equal plus or minus 1. In this case, we have two equilibrium solutions, when y equal 1 and when y equal negative 1. Remember that when we find the general solution, we will plug in the initial condition to find a particular solution. However, the solution to a differential equation also includes the interval of validity, and the interval of validity will have to include the point that is in the initial condition, in our case, the ordered pair 2, 2. Now that we've determined that we do have two equilibrium solutions, let's look for the general solution, which of course is not of the same form as the equilibrium solutions. In order to do that, we need to divide both sides by the function of y and multiply both sides by the differential dx. That is, of course, an abuse of notation. That leads to this equation that you see here in the center. After we have separated the variables into their respective sides, we integrate the two sides of the equation, the left with respect to y and the right with respect to x. Now, how are you going to integrate these? Again, you're going to have to use the techniques you learned earlier in Calculus 2. In this case, you're going to need a trig substitution. Because you have a variable thing squared minus a number, then this must be, you got it, secant. There is another option if you prefer. You could, because these represent rational functions of their respective variables, use partial fractions instead. Choose your weapon of integration. Pause the video, do the integration, then turn the video back on to compare your answer with mine. Let's see how you did. I chose for my method to do partial fractions, partly because I recognized that what I had on the left in the rational function 1 divided by y squared minus 1 was exactly the same as I had on the right, 1 divided by x squared minus 1. In that way, I could serve two purposes at the same time by solving the first one and using the same constants for a and b for the right side. I separated it into y minus 1 times the binomial factor y plus 1. I then chose to let y equal 1 and then y equal negative 1 to find those constants. I got 1/2 and negative 1/2. You can write the 1/2, of course, in the numerator, but you can also pull it to the front or pull it out completely, since in fact they're both multiples of 1/2, one being positive 1/2, the other negative 1/2. Similarly, then I could rewrite 1 divided by x squared minus 1 in the same form. That allowed me to then rewrite the integral with essentially the same thing on both sides. Now, the next step, I kind of cheated and left part of it out. It is a u substitution, where u is, in turn, y minus 1 or y plus 1 or x minus 1 or x plus 1. And it leads to 1 over u du. In that case, of course, you get the natural log of the absolute value of u. This is one that you use quite a bit, and so you should be familiar to it. In this case, you will end up with 1/2 natural log of the absolute value of y minus 1 minus the product of 1/2 times the natural log of the absolute value of y plus 1. You get something similar on the right-hand side, but with the variable x. Notice that we also get the constant of integration plus c. Now this is a long problem, so if you need more paper, pause it and go get it. In the next step, you use the log properties, which says that if you have a log of the same base and they're being subtracted, you can combine them into the log of the quotient. The one that is positive goes to the numerator, the one that is negative goes to the denominator. That allows me to rewrite the two sides into a single log. Now the next thing I'd like to do would be to equate the arguments by exponentiating both sides. However, the plus c is preventing me from doing that. The next step is something that is kind of tricky, and until you've been shown it, you wouldn't think that it would be okay to do, but in fact it is. C is a constant, and I can write that constant in any form I want, which means if I want to rewrite it as the natural log of C, where this C is a different C from that C, I can do that, because natural log of C is just a different constant representing the same decimal number. Once I write it in that form, then I can use log properties again to combine these two into the product of the constant times the absolute value. Now that I have that, you could equate the arguments, or since what you're really doing is exponentiating both sides, and the exponentiation of a natural log leads to dropping the natural log. In other words, you are equating the arguments. Now, since I have an absolute value equal to a constant times an absolute value, then there are only two possibilities. Either they're already equal or they're opposite in sign. That's the only possible way that they could be equal to one another. But hang on, I can manipulate C as much as I like, which means if they're equal, I can just drop the absolute values. And if they're opposite in sign, well, I can just roll that negative into that C. So the next C will not be this C necessarily, but it'll either be the same or the opposite. So that allows me to write the rational function on the left equal to the rational function on the right times a new constant C, where that negative that might be there is rolled into it. Now we can use the initial value that we had, that y of 2 is equal to 2. In other words, use the ordered pair 2, 2 to pin down the value of C. Doing that and plugging it into both sides of the equation you see here leads to the equation that 1/3 is equal to 1/3 times the variable C, or not variable, constant C. That means the constant C must be 1, which means that the rational functions are in fact equivalent to each other for this particular solution. Our next step is not always possible, but it is possible here, and that is to isolate y to solve for an explicit solution. In order to do that, you can cross multiply on both sides. That will lead to the following equation. Then you multiply out the two sides, and of course what you're trying to find is y, which is a function of x. So gather your y's on one side of the equation. I chose to move the y's to the left, which means anything without y will move to the right. When I subtract the xy that was on the right to move it to the left, it will cancel. In order to move the negative y that was on the right, I have to add it, and that gives me 2y on the left. Since the negative x and the negative 1 on the left do not have y's in them, then they will be moved to the right side by adding x and adding 1. When I do that, the 1's cancel and I get 2x. That means that my particular solution for this problem is the very simple equation, yes, the identity function, y equals x. Let's take a look at another example. Now that we've reviewed several of the techniques of integration, I won't go into as much detail. So for the next few examples, I will instead show you how my work, but I won't explain it in detail. Let's look at example 3. We're asked to find the general solution for this differential equation. Our steps are to isolate and find dy dx. You'll notice I paused the video because I noticed in looking at the differential equation that I was missing the differential dy. That was simply a mistake. I forgot to type it in. In this particular problem, notice that dy and the dx are already isolated. If you want to find the equilibrium solutions, you'll have to put them back together and identify your function of y and your function of x. Since they're already separated, we could look for the general solution, which is not the equilibrium solutions, by leaving them separated and making sure that we have everything involving x on the side with the differential dx and everything involving y on the side with the differential dy. We are not looking for the equilibrium solutions here. We're looking for the general. So I can ignore the first couple of steps. If, on the other hand, your directions were to solve, then you would need to look for both the equilibrium solutions and the general solution. In this case, I need to move this binomial factor 1 plus y squared raised to the 1/2 power to the right-hand side to join the differential dy. Similarly, I have to move the same factor with x instead to the left to join the differential dx. Let's accomplish that now, and then we'll get started on integrating. Now that I have isolated the two sides, I can then proceed to integrate the two sides. Notice that even though I don't have the differential isolated, I could look at this and imagine what it would be were I to move this entire thing over to the left and the differential dx back into the proper notation for dy dx. This would give me the reciprocal of this, and its zeros would become the equilibrium solutions. However, all I need to do here is find the general solution, and that means integrate the left, integrate the right, and if possible, solve for y. Go ahead and pause the video, work out the indefinite integrals, then turn the video back on to check your solution. Let's see how you did. Since the u substitution is essentially the same for both, you can do both at one time. Remember, however, that when you do that, the u on the left and the u on the right are not the same u. The one on the left involves the variable x, and the one on the right involves the variable y. In the second step, since I had a common factor of 1/2 on both sides, I chose to get rid of it by multiplying both sides of the equation by 2. The 2 you see here is not this one. It is, however, what happens when you raise the u to the negative 1/2 and increase the power by 1. That gives you the 1/2 power, and dividing by 1 is the same as multiplying by 2. That's where that 2 comes from. Now, in the next step, you have to go back to your original values for u. And again, since everything had a common factor of 2, I chose to get rid of it by dividing by 2. That means that this c divided by 2 is, of course, still a constant. So I simply rolled the divided by 2 into it and left it with plus c. This is an implicit solution to the equation. It is tempting to want to square both sides of the equation in order to, quote, solve for y. But when you square sides of an equation, it is risky behavior. Raising two sides of an equation to any even power is risky, since you can introduce false solutions because you don't get the same thing when you've got negatives involved. If, however, you are raising both sides to an odd power, well, that would be just fine, but not even powers. In this case, it is better to leave it in the implicit form and not to perhaps introduce a false solution. Let's take a look at another example. In example 4, I have changed up what the independent and dependent variables are a little bit. This is an equation that you might experience or see in a differential equations class. Q here represents quantity probably, T is probably time, and K is some unknown but real constant. In order to find the general solution, again, we don't need to consider the equilibrium solutions. Equilibrium solutions are not considered general solutions. They are the constant solutions. However, in this particular case, I could tell you where it's going to be. Remember that you have to be able to separate it into a function of t and a function of the dependent variable, which is q. In this case, there is no t present in the entire equation other than in the differential. That makes this an autonomous equation. And these, of course, are very simple to do by separating variables. However, the equilibrium solution would come from q minus 70 equal to 0, which is when q is 70. So 70 would be our equilibrium solution. To find the general solution, we need to separate the variables. That means that you need to move the differential dt to the right and the q minus 70 binomial factor to the left, and then integrate. This will lead to the integral of dq over q minus 70 equal to the integral of k dt. Remember that k is some unknown real constant. You would again use u substitution on the left, but this is such a simple u substitution, it's hardly worth writing it all down. Since the derivative of u with respect to q would just be dq, and since the integral would then become 1 over u du when you substitute, you could skip all the interim steps and simply write down the natural log of the absolute value of u, which is, of course, q minus 70. It does produce a constant of integration, but you're going to roll it into the side where the independent variable, in this case t, is located. This would give me kt plus some constant, which is really a combination of two constants of integration. Now, could you solve this one for q? Yes, you could by switching this into its exponential form. Let's take a look at what that would look like. That means the base e is being raised to the kt plus the constant power, and it's equal to q minus 70. To solve for q, you'd add 70 to both sides. But hang on, we can do more. We can write e to the kt plus c as e to the kt times e to the c. Now, why would I want to do that? Remember, we're trying to get this into the most general format we can, and it's simpler if the constant is either a term being added or a factor being multiplied. Not so handy when it is a term in the power on an exponential. But e to the c is, yeah, you got it. It's just a constant. So what we'll do is we'll write that in a different form, which looks like c e to the kt plus 70 equal to q of t. That is our explicit general form for the solution to that differential equation. Now, I have made an assumption here that you can't necessarily make. In this case, I assume that q would come out to be larger than 70, meaning that q minus 70 is strictly positive. If that cannot be assumed, then you will have to keep the absolute values around the q minus 70. This, of course, assumes that q is greater than 70 in order to write it in this format. If that's not an assumption you can make, then you won't be able to go as far and you won't get an explicit solution, but you'll get very close. Instead, starting back here at this step, you would write e to the kt. Again, you would switch the e to the c to a constant factor, but you would leave the 70 and the q inside the absolute values. This is not an explicit formula. It is implicit because you won't be able to remove this from the absolute values unless, of course, you chose to write it in terms of a piecewise defined function. If you want to write it as a piecewise defined function, then you could write it again explicitly. In that case, you would write the following: that q of t would be equal to the piecewise defined function that you have c e to the kt plus 70 for the cases where q is greater than or equal to 70, and that you would have minus c e to the kt plus the 70 in the cases where q was less than 70. Now you may say, but hang on, I can roll that negative into c e to the kt. And indeed you can, but if you do that, you'll lose the fact that you have to be careful about the fact that q may or may not be greater than 70. So I wouldn't recommend doing it. Let's take a look now at an initial value problem, which is example 5. In this problem, we want to take a closer look at that interval of validity, or the domain of the solution. That's not something I'm going to test you on in a Calculus 2 class, but it is a very important part of the solution in a differential equations course, and I feel I would be remiss if I didn't at least emphasize it a couple of times. So let's take a look at this problem. I have dr d theta equal to r squared divided by theta, and I'm told that r of 1 is equal to 2. In this case, I know that the dependent variable must be r because it is written in what would be considered the numerator of that notation, and that theta must be the independent variable because it is written in the denominator of what would be considered that notation. This looks like probably something in the polar coordinate system. However, that's not going to affect our steps at all. I want to solve it, which means I also need to consider those equilibrium solutions. If it doesn't say find the general solution, then they want all solutions. That means equilibrium and general. To find the equilibrium solutions, remember I need to separate it into the two pieces, but essentially it already is. I can think of this as a function of theta times a function of r if I simply write it as 1 over theta times r squared. That separates the two. Now let's take a look at the next step. That allows me to find the equilibrium solutions. When I'm looking for the equilibrium solutions, remember that you take only the function of the dependent variable, in this case g of r, and set it equal to 0. This tells me that r squared equals 0, which happens, of course, when r is 0. That is my equilibrium solution. That's one of them. Go ahead and box it up before you forget it. Now let's take a look for the general solution. If we're going to look for the general solution, then I need to separate the variables if possible and independently take the antiderivative of both sides of the equation. Looking at the equation, that means r squared needs to go left to join the differential dr, and theta can stay where it is, while the differential d theta needs to move to the right to join it. This leads to the following. I will get, wrong variable. I will get dr divided by r squared equal to, on the right side, d theta divided by theta. D theta divided by theta is, of course, going to give me the natural log of the absolute value of theta plus some constant. On the left, I can think of dr over r squared instead as the integral of r to the negative 2. That leads to r to the negative 1 times a negative 1, also plus a constant, which I'll roll into the constant on the right. This lets me write negative 1 over r equal to the natural log of the absolute value of theta plus some constant. Now, in this particular problem, we do have an initial value or an initial condition. R of 1 is equal to 2. Remember that that 1 is the angle theta, and that 1 is represented in radians. In this case, we need to replace theta with 1 and r with 2. This leads to 1 over r equal to the natural log of the absolute value of 1 plus the constant. Now the natural log of 1, that's 0. Now I forgot to replace the r with 2, so let's go ahead and do that now. That tells me that the constant must be, in fact, negative 1/2. Let's rewrite our general solution with that value plugged in place of c. This gives me negative 1 over r equal to the natural log of the absolute value of theta minus 1/2. Now, can we get this in a better format, and can we solve it for r? We would like to be able to do that by possibly, and this is something you may want to consider or not, rolling this minus 1/2 into the natural log. Now, you could do that, but of course it's not required. This leads to the following equation for r. R is equal to 1 divided by the quantity 1/2 minus the natural log of the absolute value of theta. Now there are a couple of problems we need to worry about here since we're worrying about the interval of validity or the domain of the solution. First off, I should be sure, because of natural log, that theta is not 0. So I need to tuck into my head over here somewhere that theta cannot be 0, for the simple reason that natural log will not accept 0 as an argument. It also will not accept negative values, but because of the absolute value, I don't have to worry about that. I do, however, have to worry about the fact that this appears in the denominator. Thou shalt not divide by 0. So I need to make sure that 1/2 minus the natural log of the absolute value of theta does not turn out to be 0. Let's use the algebra to figure that out. By setting the denominator equal to 0, I'm able to solve after switching from logarithmic form into exponential form for the value that theta should not be plus or minus e to the 1/2 power, or e underneath the square root. This is going to divide up the real number line into 4 different sections. 1, because theta cannot be 0 because natural log will not accept 0 as an argument, and because I cannot allow the value of theta to be plus or minus the square root of e either. Let's take a look at the real number line and think about what this does to it. If I have the real number line, somewhere I have 0, and I know that can't be used. Somewhere to the right, I've got the square root of e, whatever that happens to be. And the same distance to the left of 0, I have negative the square root of e. This gives me my 4 regions where I could find the solution. From negative infinity up to negative square root of e, between negative square root of e and 0, between 0 and square root of e, and from the square root of e to positive infinity. This, however, was an initial value problem. Where is my point? Where's my initial value? Scroll back up and let's pick up what that initial value was. That's 1, 2. We need to pick the interval in which that point lies. That is the particular solution and its interval of validity, or where it is the solution. Where would 1, 2 fall on this number line? To figure that out, you're going to have to know what the square root of e is. You can grab your calculator and figure it out. Or you can simply wait, and I'll tell you that it's about 1.65. Since this is roughly 1.65, that means that my particular initial value, that theta is 1, must fall in this region right here. Here's 1, so it's got to be somewhere in here. Therefore, my interval of validity will be from 0 to the square root of e. We have one last example before we'll end this video. We want to solve this initial value problem and consider its interval of validity if we can. In this case, we already have isolated dy dx. We will need to separate the dependent variable parts, which are dependent on y, from the independent variable parts, which are dependent on, in this case, should be t. I'll correct the differential now. Now that I've corrected the differential and the independent variable is t everywhere, we do need to consider the equilibrium solutions because it simply said solve, not find the general solution. In this case, I need to rewrite the exponential e to the power y minus t in a different form. This gives me dy dt equal to e to the y times e to the negative t. Same base, add the powers. This is multiplied by the secant of y, which is also multiplied by 1 plus t squared. Let's separate the parts that depend on y from the parts that depend on t, and double check to make sure that they are in fact multiplied together. If I write those in purple and I write the ones dependent on t in red, this gives me 1 plus t squared divided by e to the t. It is separable. Moreover, I can look at this part here and I can determine the equilibrium solutions by setting the part dependent on the dependent variable y equal to 0. An exponential will never give you 0 unless it's been shifted. In this case, our solutions for the equilibrium will come from secant of y. When is secant of y equal to 0? And the answer, of course, is it's not. Remember that when we're looking for the equilibrium solutions, we're setting that function of the dependent variable, usually y, equal to 0. However, e to the y is never 0. That will not give me any solutions. Secant can be written as 1 over the cosine of y, but that is never 0, since the only way to get a fraction to be equal to 0 is for the numerator to be 0 and the denominator not to be 0. But 1 will never equal 0. So I have no equilibrium solutions for this particular problem. Now that we've identified, however, the function of y and the function of t, let's separate them and integrate. Pause the video, work out the integrals, then turn the video back on to check your answer. Let's see how you did. This is a pretty long problem that involves integration by parts on both pieces. We'll start on this particular one by doing them separately. I chose to do the one with respect to y first, and I'll leave the one with respect to t to follow it. I did them again in color-coded so that the one with respect to y is in purple and the one with respect to t is largely in red. When you do this, again, I used the tabular method for integration by parts. Notice, however, that because one of the functions is cosine, that I will not get the u part to 0 out. Instead, I go until I get a multiple of cosine, and then I stop. Remember to alternate the signs, and that the last one, the product of the bottom row, is of course an integral itself. Since this is one of the ones that repeats, I need to write the original integral on the far left. That's what you see here. Then it's equal to the product of the diagonals, and then with the integral of the bottom row at the end. Working out the signs, that leads me to this expression. Notice that this one is the opposite of the original integral I was looking for. This should happen on all the ones that repeat. I can add the integral to both sides of the equation, which gives me 2 of that integral. Then I will be able to divide by 2. Notice I had to put in the constant of integration since this is an indefinite integral. When I divide by 2, dividing the constant by 2 is still constant, so I can just leave it plus c, though of course it's not exactly the same number as this one. Then I can factor out the 1/2 and the e to the negative y, which are constant factors, and a factor which depends on y. The squiggly pink line is just to separate the part that has to do with the function of y from the part that is the function of t. In the next part, I again did integration by parts. That's because this is a polynomial in t and the other is an exponential in t. Then I will choose the polynomial part to be u. You take the derivative of the u side until it either zeroes out or you get a multiple of the original u. In this case, it zeroes out. And dv is going to be whatever part is left, in this case, the exponential. Notice that the zeroing out are the most favorite ones to do for tabular because the bottom row, which represents the integral which has not been done, is zeroed out too, and that means I don't have to integrate again. By multiplying this out, I was left with this expression that you see on the right. I distributed and combined like terms, and then I noticed that all of these in the parentheses were negative, so in the next step, I went ahead and factored that negative out so that I could have the polynomial in parentheses in terms of positives only. Now we need to put the pieces together again. Putting the pieces together, you'll see the left side is in purple coming from the integral with respect to y, and the right side is in red coming from the integral with respect to t. Notice that these constants on the left and the right will not cancel because they're not the same constant. Don't make that mistake. Then, once I combine them together by moving the constant of integration with respect to y to the right side to join the constant of integration with respect to t, that gives me a different constant of integration, which is this one down here. Now this gives me an implicit general solution to the equation. It's general because I still have the constant plus c. It's implicit because I cannot solve for y. I cannot get it out of the exponential and out of both trig functions at the same time. It's not going to happen. You're not going to get an explicit solution. To solve the initial value problem, we need to now apply our initial value that when t equals 0, y equals 0. Plugging these in leads to the realization that the constant must be 5/2. To find the particular solution, replace the constant with 5/2. This will give you an implicit particular solution. Now, we need to consider the interval of validity. Unfortunately, trying to determine the interval of validity or the domain of the solution from an implicit solution can be quite difficult and something better reserved for the actual differential equations course. So we'll skip it here. This is the last example in this video. I hope that you have learned something about how to use separation of variables to solve differential equations, and this ends the video.